Let's see how long it takes to actually stop smoking. So with our powers combined, this is a part that's printed in the x-axis. Thanks for watching. What a mess.
Today we're going to be diving into a material that's lightweight, rigid, and perfect for industrial parts. Carbon fiber reinforced nylon 6, otherwise known as CFPA6. Note that there's also nylon 12 and also a nylon 11, which we'll get into in a future video. Whether you're in automotive, aerospace, robotics, or general manufacturing, CFPA6 offers a strong balance between strength, printability, and heat resistance without the insane price tag of something like PEEK. CFPA6 stands for Carbon Fiber Reinforced Polyamide 6. Basically, it's a nylon that's been toughened up with chopped carbon fiber. Now, nylon alone is already everywhere. It's one of the most widely used polymers in the world. You'll find it in automotive parts, consumer products, textiles, electronics housings, industrial fasteners, and thousands of applications. It's been injection molded into millions, if not billions of parts over decades. What makes CFPA6 exciting in the context of 3D printing is how additive manufacturing opens up design freedom and production flexibility, especially for low-volume functional parts. This filament is perfect for those looking for a material with a high modulus, improved chemical and thermal resistance, excellent surface quality, and ease of printing. Instead of needing tooling or molds, you can now create strong, thermally stable nylon composites directly from your production 3D printer, like our 22 IDEX. The carbon fibers reduce warping, improve dimensional accuracy, and boost overall rigidity. It is a smart material for engineers who need fast prototyping, jigs and fixtures, or end-use parts that don't quite need aerospace tier specs, but still need to perform. You can get a lot of the same benefits you'd expect from an injection molded part, minus the lead time and cost. And if you want a real-world benchmark, take a look at the current Formula One Constructors champions, McLaren. The Woking-based team has always been at the forefront of technology in motorsports, and 3D printing is no exception. Together with technical partner and sponsor Stratasys, their engineers were able to swap out traditional composite fabrication for FDM Nylon 12CF to print strong, race-ready aerodynamic parts in just 5 days. That same process used to take nearly a month with conventional methods. Not only did they slash lead times by 60%, they also saved over 25% in cost. For parts like front brake ducts, 3D printing wasn't just faster, it was 86% cheaper. And even their pit tooling and brake wing components are printed from composite thermoplastics. The lesson? Whether you're building cars, tools, or fixtures, additive manufacturing with CFPA6 opens up a new tier of speed, performance, and affordability. And with a 22 IDEX in your corner, you're equipped to print these same kinds of production-grade parts right from your shop. Visit visionminer.com for more info. Another standout example is their custom engine bay cooling ducts, which were produced on demand between race sessions. These parts route airflow through narrow channels in the chassis to keep the engine cool while the car is idling, a job typically handled by fragile composites or expensive custom tooling. CFPA6 thermoplastics let them print these ducts fast and install them the same day and avoid costly mold development. And even off the car, McLaren put CFPA6-like materials to work. They printed protective shrouds for their pit grew wheel guns, covering expensive electro-pneumatic tools with rugged ergonomic casings that can withstand repeated impacts. These aren't just props, they're used in actual races where milliseconds matter. If you need a material that can do structural brackets, cooling ducts, functional tooling, or ergonomic housings, and you need it now, CFPA6 is ready for the job. And if you're ready to take the plunge and try out CFPA6 for yourself, we sell this material and the entire 3DX Tech lineup on our website at visionminer.com. Fancy yourself a 3D printer instead? Well, we carry 3 different kinds of 3D printing technologies like our venerable 22 IDEX that we use to print all of these parts that you see in our videos. Give us a call or shoot us an email and we'll help you get started today. So in front of me on the table, you will see that I have selected a couple of CFPA6 parts. And one thing you'll notice is they're all gigantic. This NACA duct that I have in my hands right here, which you may remember from a video we did last year, is a great example, great use case for CFPA6. If I recall, this part was tuned within 3 prints. It was relatively easy because it's CFPA6. It's really easy to print, guys, and it prints beautifully on the 22 IDEX back there. This part is relatively rigid. It's not like so rigid that if I were to smack it, it would shatter into a million pieces, but it holds its shape. It'll hold its shape under heat. It'll hold its shape in the sun, on track. It'll withstand vibrations and whatnot, and yeah, pretty tough. Another part I have here is this CFPA6 generative design early prototype for a camera mount for our 22 IDEX. It's held on with magnets and it has just enough structure to hold a Canon Rebel T3i. A prototype just for fun. Here's what works for us when printing CFPA6. Nozzle temp, 275 degrees Celsius. Bed temp, 80 degrees Celsius. Chamber temp. Although a heated chamber is not necessarily needed, we highly recommend it, especially when you're printing parts this big. Filament drying, 80 degrees Celsius for at least 4 hours. Nylon absorbs moisture very fast, and if you skip this step, your surface finish and strength will take a serious hit. And on another note, with all composite materials that we keep mentioning, you should use a hardened steel nozzle. Brass won't last that long. Use a carbon fiber build plate and Vision Miner nanopolymer adhesive for excellent layer adhesion and clean removal. Here's what you're working with when printing CFPA6. Tensile strength, 63 megapascals. This measures how much pulling force the material can take before it breaks. It tells you how well your part will handle axial loads. Tensile Modulus, 3800 megapascals. This is a measure of stiffness under tension. A higher number means less stretching or deformation under load. Flexural strength, 84 megapascals. This indicates how much stress a part can withstand while being bent. It's crucial for cantilever brackets and load-bearing structures. Flexural Modulus, 3,750 megapascals. This tells you how resistant the material is to bending. Parts that need to maintain shape under pressure benefit from a high flexural modulus. Elongation at break, 3%. This measures ductility. Lower values like this indicate a stiff but more brittle part that won't stretch much before breaking. Heat deflection temperature at 0.45 megapascals, 147 degrees Celsius. This is a temperature at which the part begins to deform under a small load. It tells you how hot your part can get before it starts to lose its shape. Glass transition temperature, 70 degrees Celsius. Below this temperature, the polymer remains glassy and rigid. Above it, the material becomes more rubbery. This is important for thermal cycling environments. Surface resistance, 10 to the power of 9 ohms squared. This measures electrical conductivity. A value like this means it can safely dissipate static charges. Great for electronics and ESD-safe tooling. Note there's also ESD-safe specific nylons, which we'll get into in a later video. Density, 1.17 grams per cubic centimeter. Lower density means lighter parts. It's a great balance between weight savings and structural rigidity. These specs put CFPA6 squarely in the performance polymer category. While it's not peak or ULTEM, it's well above hobby-grade materials. Let's compare CFPA6 to a couple materials you might be considering for functional prints, ULTEM 9085 on the high end and PETG on the lower end. ULTEM is one of the gold standards for high-temp aerospace-grade parts. It's FST rated, it's strong, extremely heat-resistant, but also requires a high-end machine, specialized printing conditions, and comes at a premium price. Now, if your parts don't need to meet FAA or spaceflight level requirements and don't need to meet the rigors of strong acids, oils, and hydrocarbons, CFPA6 gets you great strength, moderate chemical resistance, and dimensional stability at a fraction of the cost. Did I mention it's also significantly easier to print? PETG is great for hobby products and light-duty enclosures. It's affordable, it's easy to print, and decently strong, but it just doesn't compare in terms of the rigidity, thermal resistance, or long-term part accuracy. PETG will deform under load or heat, whereas CFPA6 stays solid. The bottom line is, CFPA6 is that sweet spot. It gives you a real boost in performance without the complexity or the cost of high-temperature polymers. It's not going to Mars, but it'll handle most shop floors, automotive, robotics, or industrial use cases without breaking a sweat. CFPA6 is an incredibly versatile material, ideal for functional components that need to take real-world abuse. One of the biggest markets for this material is the automotive industry. Whether it's under-the-hood components or even ducting components, CFPA6 handles vibration, thermal cycling, and mechanical stress with ease. If you're working on custom cars, motorsports projects, or building short-run production parts, CFPA6 offers the performance of injection-molded components without the need for tooling. I've been using CFPA6 parts to mount various components like my CalDigit TS3 Plus on the bottom of my desk because the material prints so well and has plenty of heat resistance to withstand computer components. I've had this part since 2020, making it about 5 years now, and the only reason I'm replacing it is because I got a new desk and I wanted to print another one. In manufacturing and robotics, CFPA6 excels at creating jigs and fixtures, end effectors, and structural arms that will stay stiff over time. We've had customers replace aluminum tooling plates with CFPA6 parts on their production lines, not only cutting weight, but also saving on machining lead times. The material's dimensional stability and resistance to creep under load make it ideal for repeat use environments where accuracy matters. So, now that you know what CFPA6 is, where to use it, and how to print it, let's see how it performs in the real world. We're going to hand it over to Cole to put this stuff to the test. Strength, heat, and maybe even a few burns. Let's jump in.
Matt, who's behind the camera right now, thank you very much for educating us on nylon and its uses. Super common material, not the most common. I'm here to show you what it can actually do. What does all of these facts and numbers mean? Let's put this material through its paces. As usual, we're going to UTM, Universal Testing Machine, torsion test. We're gonna light it on fire. This time I did something special. I've got both blue and yellow is hotter. MAP gas and propane. Oh, special treat, I annealed these parts. Well, let's just start with the 1 inch away for 5 seconds is our baseline to see what this material actually does. That behaved a lot better than I thought it would. I got to turn this fan off. Got to see the smoke. That did very well. It self-extinguished very quickly as well. Let's try some MAP gas. Brought this from my own home personal stash. This is the good stuff. And that's what we don't want to see. Burning like a candle. Literally, yeah. Self-extinguishes pretty quickly, but I think if you give this enough heat and time, it's just gonna stay lit. Oh man, I know that smell all too well. There we go, drip. That's the downside of nylon. Let's see how long it takes to actually stop smoking. So, all right, so there's your answer. We're gonna turn on the fan real quick. We'll be right back, because this is bad. Oh, so that didn't do very well in my opinion. Here is some peak that we did a while ago. We'll do this with, I haven't done this with MAP yet, so. And it's out, and it stopped smoking. That's the difference. This is peak, right? No, this is 9085, and it doesn't matter. Printing with the 22 is what gave us the ability to print these exotic engineering grade materials. That's why these are used in aerospace. Off-gassing in a vacuum, self-extinguishing. Can you imagine how much of a mess burning nylon would make in terms of fumes in a pressurized cockpit? Whereas this guy, we're gonna head over into the next studio to use our, don't do that. Don't. Fine, we're gonna use the vise on the end of the table to see the torque readings. All right, we got our torsion testing specimens and a torque wrench. Let's see how these do. 14.8, nylon keeps impressing. Look at that break. That's what you want to see, because there's absolutely no weakness in the Z. If there was any printing issues, it would have broken along a layer line, but this sheared laterally. Let's get one more for baseline, and just to make sure that we're getting consistency. 4.6. That's the worst case scenario, the way that broke. For obvious reasons, it broke along a specific layer. Uh-oh, I think, I know what's happening. The strong one was printed on the 22. The rest of these were printed them at home, not on the 22.
That's a good selling point.
Wow. Why do you need a 22 IDEX? Well, dude, 13.6. These are printed at home on my not real high temp machine. And these are printed on the 22. There you go. What else do I need to say? That's crazy. Here's the annealed part. Yep, this is going to be on my printer at home. Even though it's annealed, it's going to suck. Wow, that's fascinating. Why did the 22 print it better? Well, chamber temperature is a big one. Those crappy ones, those were printed on a Creality at my house with a chamber heater in it. I did not expect that kind of a result. Combination of LGX and high quality slice hot ends. I definitely trust the actual temperature management and feed rates. More powerful heaters, but mainly it's the idea of an actually actively high-powered heated chamber. 22, other. And this isn't an unattainable material, this is nylon. This is PA6 CF. People are printing these all the time on their bamboos and Crealities and stuff, but that's what a proper industrial machine does. I want to know what the UTM results actually show, and I'm learning a shocking amount. Okay, Nylon PA6. Everybody's favorite. Nylon, the man, the myth, the legend. We're climbing past 1,000, up to 1,200. How far will it go? Nylon is impressively strong. Okay, so we maxed out at 1416 for the X and Y. One thing about nylon is that it always behaves the way you expect it to behave. Once you've used it for a while, you just know how it's going to want to print, how it's going to want to be oriented, how strong it is. I bet you these numbers are pretty dang close. Bang. 1468, that's consistency right there. Now for the Z. The Z is always a disappointment. I hate to admit it, but let's see. Break 1,000. There, very good. Just barely. 1,068.7. Not too bad. Not great, but not too bad. And just for consistency, we're going to do it again. Just past 1,000. Is it going to keep going? No, that is consistency right there. Oh boy, that was only a 6 difference. I actually got curious about annealing, so I threw some of these tensile bars into our heated oven for an 80°C for about 12 hours. I am blown away by this. 2,145 just by throwing it in the oven for a while. Let's look at the microscope. This is the part that I melted, and it melted real weird. Look at that. Autofocus, please. Autofocus. As you can see, this is one giant disgusting blob. And that's because nylon is not a super material like this 9085. This is very clearly melted. This is very clearly burned. I find that fascinating because I can't scrape off the melt. Where's my knife? Who knows? Knife's gone. This obviously got completely deformed. There's charring on it, obviously, but you can tell how it dripped down itself very clearly. This stuff likes to drip. So if you see this pattern here, I like to call this logging because it looks like the trunk of a tree. I made that up, but we're going to start using it. This is the torsion test that was printed on the 22, and that's what you want to see. This is the part that's printed in the x-axis, top to bottom. It's not flat like that. It's like that. That's always going to be weaker. This part, the 22 part, ignored the fact that the z-axis is supposed to be the weakest, and it sheared in the x and y. Even though this is printed in the z-axis, showing that it has awesome, immaculate, impeccable layer adhesion and strength. Here's a part that was printed on a lesser machine. You see what I'm getting at there? Very clear weak point, which is the entire z-axis. This is the result you want to see to know you have a strong z-axis stability. What do you want?
No, just keep going. You're good.
Okay. I printed some of these at home, and I don't have a 22. And if you want to see me have a 22, comment down below, give Cole a free 22. There's a nylon for you. Does it perform like an ULTEM 9085? No. It's about a quarter the price. And it's accessible. And it can be printed on a bamboo or a creality, even though I wouldn't. So I don't want you guys to think for any reason that nylon is not an amazing magic material. If you want to buy a 3D printer that's going to be the last 3D printer you ever buy, then call us and buy a 22. You want SLS? We got that. You want SLA? We got that. You want filament? We got everything. We have everything. We don't have binder jet. Yeah, we don't have binder jet, and we don't have metal. Okay, give me a break. This is just the beginning of this testing series. We have very dangerous chemicals, extremely high pressures, and it's going to get a lot more reckless and dangerous. I got a machete here. I'm going to incorporate the machete at some point. Not yet. Find another channel that's using the machete on plastic. The difference is we're writing numbers down, so it's science instead of just messing around. See you next time. Buy the 22 IDEX. It's really good. Hey guys, as a special bonus for all of our subscribers that stick around to the end, I'm just going to absolutely decimate this ABS part with a machete. It's science. I know how to make this better. With our powers combined, Off, 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 off. Firepower. Yeah. I got problems. Thanks for watching. What a mess.